So here's an odd one. And I say it's odd because I've only ever seen this done with computational work. And we require students to know it, and it's a useful skill, but I say it's a useful skill knowing I only ever use it because I did calculations. So there is one other way to find EA, the activation barrier, and it's a really easy way, super simple, but even though it seems really obvious, we probably should talk about it. I showed you some earlier diagrams where we had energy versus reaction coordinate. And I showed you that you have the reactants. They go up and you form products. And this is your transition state. Well, we can actually, if we know this plot versus reaction coordinate, we can figure out the activation barrier directly. Now, this is typically not done in practice because it's really hard to generate these plots without using a lot of computational work. But let's say for sake of argument you see it as a problem, and you will in tests, you'll see it it's actually quite a bit. The reactions sit at some energy level, E1. Our transition state sits at some level, E2. So our activation barrier, EA, is simply E2 minus E1. And this should always give you a positive number. It always takes energy to go up to the transition state. So our EA is simply the difference in the height of the energy of the transition state and the energy of the products. Reactants. Now the reason I tell you this is that reactants aren't always set to 0. Sometimes they may be greater than 0, sometimes they may be lower than 0, depending on what scale we're working with. We don't care about where E1 and E2 sit exactly in the energy scale. What we care about their relative differences. So when you find this EA, it's not just the E2, it's not the energy of the transition state, it's always the energy of the transition state minus the energy of the reactants.